All righty. Okay, so I picked out a few. Let me get my version of the hard copy here and keep us in line. Okay, and then I'll use this whiteboard to discuss things. Okay, let's do number 1. So this is chapter 10. Number 1. Which of the following should have the lowest boiling point? Excuse me. No. Okay, of these 5 choices, which should have the lowest boiling point? No, that didn't do it. Hold on. That's why I hate working from home. Too many distractions. All right, we got these 5. That one, sodium sulfide, hydrogen fluoride, NH3, ammonia, nitrogen, and water. Okay. Since we're not given any information about the boiling points themselves, right, and technically we can't look them up because we would be in the middle of an exam and you can only have the information that's provided to you, we've got to reason it out. So the first thing I do is see if there are any high boiling point compounds here. That would be ionic compounds. In fact, there is one. This one is ionic. It's going to have the highest boiling point of all of them. And don't get these confused with, say, that one with an acid dissolved in water. It's not. This is hydrogen fluoride gas. It's not dissolved in water. So this one is the highest. We can eliminate that one. Now, I could go straight. I see a way to go straight to the lowest boiling, the easy way. But what I'd like to do is investigate this in terms of intermolecular forces. What's holding these things together? This is ionic bonding. That's why it's the strongest. It's going to be the highest boiling point. The next strongest is dipole interactions. And then there's the strong end of the dipoles would be hydrogen bonding, right? And as a matter of fact, each one of these, that one, and that one, have the potential for hydrogen bonding. So we've got to decide which one is the strongest. So this one would be like that, and the dipole would be like that. Okay? This one, water, would be like this, and individual dipoles would be like that, and then overall dipole would be like that. Ammonia is like this, right? And the dipoles are like that. Okay. I heard my doorbell and I just wanted to listen to see if anybody's going to answer it. Okay. So now, which are the strongest dipoles of these? Well, the electronegativity tells you the strength of the dipole, especially since each one of these is hydrogen bound, right? Obviously, since it's hydrogen bonding. No, no one's answering. I'll be right back. All right. I'll be sure and chop out those interruptions when I process the video. Okay, back to our talk of hydrogen bonding. All of these electronegative elements are bound to hydrogen. So all we need to do is say, first of all, what's the strength, the electronegativity of each one? Well, we know based upon the trends of periodic table, right? So we've got, let's see, here we go. Nitrogen, oxygen, fluorine. So fluorine is the most electronegative, oxygen's next, and nitrogen's next. So the individual bonds, this one is the strongest dipole, then this one, and then that one. The problem is, this has only got one dipole. This one's got two that vector add together to give you the overall. And this one's got three. Plus it's got a lone pair. Well, this one's got two lone pairs up here. Okay. So the end result is, instead of this one having the strongest dipole overall, and this one having the weakest, it's the other way around, because this one only has one, this one's got two, and this one's got three. But as it turns out, while they have different boiling points, and this one has the highest boiling point of the three, this one has let's see, it's a toss-up between these two. I'm thinking this one is the next, and then this one. Anyway, be that as it may, we don't have to decide which one is which. We just have to say, this one's the strongest, these three are in the middle, and this one is the weakest force, because these are hydrogen bonds, this is ionic, and that one is my mind's gone blank again. Well, shoot. It doesn't say in my review document, does it? I keep wanting to say van der Waals, but that's not it. That's what happens when you get old. Anyway, this one is completely symmetrical. London dispersion forces. This one has the weakest force, so it's going to have the lowest boiling point, nitrogen. In fact, its boiling point is minus 195 degrees Celsius. It's definitely the coldest one in there, if it's a liquid. So the answer to this one is D, based upon those study of the intermolecular forces. All right, next one on my list is 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Okay. Hydrogen bond, here, here, here. This is going to be slightly positive, and this will be slightly negative. Okay, so we know which direction the dipole is going. Now, when they actually interact, which molecules interact with which? Well, it's got to be electrostatic. The negative side interacts with the positive side. So they're going to line up like this, because this one's negative. Like that, like that. So it's the positive hydrogen with the negative oxygen. Slight positive, slight negative. So let's see which one works. Hydrogen from one molecule and no, 2 hydrogens don't interact. Hydrogen from one and an oxygen from the other. There you go. Right. That's your answer. Let's see, how about uh, 4? Okay, I may not be able to get the whole thing on here. Consider the representations below to answer the following question. All right, so this is going to be number 4. And Roman numeral 1. Let's go down to the question and see which one we need to look at. Which of the following statements are incorrect concerning drawing 3? All right, so we don't need to look at the other guys, just 3. Well, let's see what we've got here. What does it look like? It looks like we've got a chlorine and we've got hydrogens. So this is hydrogen chloride, and it's drawn correctly. The hydrogen is the positive side, the chlorine is the negative side. And it looks like they're correctly lined up. Negative, positive. There's a negative, positive. There's a positive, negative. Okay. Which of the following is incorrect? Well, it says, E says there 2 of the above statements are incorrect. So we got to look at all of them. So A says the electrostatic interactions exist between the molecules. Well, that's true. These are electrostatic. They're not complete ions, but they're still slight negative, slight positive. So you do get electrostatic interactions. So that was true. B, the molecules find the best compromise between attraction and repulsion. That's also true, because if they're constantly in motion. So if a negative approaches a negative, it's going to repel. But when a positive approaches a negative, they get some attraction and they tend to stay close to one another until the others line up. So what they're doing, and what that statement actually says, is when it says the best compromise, the system is finding the lowest possible energy. Everything tends toward the least energy. That means stability. So A and B are both true. C, these molecules exhibit ionic bonding. False. We have no ions in this mixture. D, OCS exhibits this type of interaction. So what do they mean by OCS? They mean oxygen, carbon, sulfur. Okay. So if we could draw the Lewis dot structure for this, but I don't think it's necessary. We just need to know the order. It's oxygen, then carbon, then sulfur. So oxygen and carbon are different electronegativities. So you're going to get a dipole this way. And sulfur would be that way. But sulfur is weaker electronegative. So we could draw the dot structure, but this will tell us what we need to know. Even if it is linear, and I'm not saying it is, but even if it is linear, the electrostatic, the slight negative charge on this side is bigger than the slight negative on that side. So it's going to be overall that direction. So that means you do get a difference. You get a separation here, and this is slight positive. So you can get the same type of electrostatic interactions for this molecule as you can for hydrogen chloride. So that means, well, if that's true, then two of the above, oh no, are incorrect. D is true, A is true, B is true, C is the only one that's not correct. So C is your answer. How about 5? The freezing point of helium is minus 270 degrees Celsius, right? What's absolute zero is minus 273. So it's pretty close. If we round it off, it's either minus 3, it's either 3 or 4 K. It's in that neighborhood. It's really cold. In fact, I think liquid freezing point, yeah, that should be the coldest bulk substance that we can create. The freezing point of xenon is minus 112, so freezing point is much higher. Both of these are in the noble gas family, okay? Which of the following statements is supported by these data? Helium and xenon form highly polar molecules. That's false. They can't form polar molecules, right? Because they're individual atoms. So they're not bound to anything else. A is false. How about B? As the molecular weight of the noble gas increases, the freezing point decreases. It's just the opposite. If we go from helium down to xenon in the periodic table, the molecular weight or the molar mass increases. And as you increase the molar mass, the freezing point increases also. So B is false. London dispersion forces between the helium molecules are greater than the London dispersion between the xenon molecules. Okay, think about this. As the force of attraction increases, what happens to the boiling point, the freezing point? The freezing point has to increase as the force of attraction increases. So the London dispersion forces between helium molecules are greater than the London dispersion between, no, it's the other way around. The London dispersion forces holding the xenon atoms, it shouldn't say molecules, atoms together are greater for xenon because the freezing point is also greater. So C is false. How about D? The London dispersion forces between helium molecules are less than the dispersion forces for xenon molecules. That is true. That follows from the data. Now, why is that? That's because this is a tiny atom, and that's a big atom. And the more electrons and the more room there is to move around, the more apt you are to have uneven distribution of electron density. That's why you get instantaneous differences in electron distribution in larger molecules than you do in smaller molecules. And that's exhibited by their intermolecular forces and the behavior that shows. Okay, that's the point of that question. About 6. All right. Yes, that's one of my choices. Which best explains the following trend? This is kind of like the same line of reasoning as 5. These are all noble gases, and they're increasing in mass as we go down: helium, neon, argon, krypton, xenon. And the boiling point in Kelvin is increasing. So how do we explain that? Well, with the same reasoning that I just gave for number 5, as you increase the size of the atom, you increase the strength of the London dispersion forces, which is exhibited by an increasing boiling point. So London dispersion is the answer to that one. Yes, 7. Which of the following compounds has the lowest viscosity? Okay, lowest viscosity. Remember what viscosity is? It's the viscosity is a measure of the passage of a liquid through an orifice. So low viscosity means it goes through fast. It's like pouring water through a sieve. High viscosity means it goes through slow. So high viscosity would be like honey trying to get through that sieve. Okay, so what's the difference? What makes the difference between low and high viscosity? Low viscosity means the intermolecular forces are very low. High viscosity means the forces are high. So we need to look at these possibilities and say, which one has the lowest intermolecular force? Well, we can count HCl out because it's polar. We can count water out because it's polar. Now these, carbon tetrachloride, nitrogen, and this compound, which is, let's see, well, it's a long chain hydrocarbon, right? This internal group here times 25, it's a long molecule. It's like axle grease. So it has very high viscosity. And it has high viscosity because the London dispersion forces for this molecule are also great. So what's left? Well, the nonpolars here, carbon tetrachloride, but carbon tetrachloride is a big molecule. So the opportunity for London dispersion forces is much greater for this nonpolar molecule than it is for this smaller one. So the lowest viscosity should be this one, nitrogen. Well, another way to look at it, let's approach it from a different angle. What's the viscosity of a liquid versus a gas? gases have the lowest viscosities. Right? So how many gases do you have? Well, you got this gas here and you got that gas there. Right? So we can compare those two gases. The viscosity, in fact, it may seem strange, but you can measure the viscosity of a gas. And the viscosity of HCl is going to be much higher than N2 because HCl is a polar molecule. Okay, there's two ways to deal with it. How about number 8? When a non-polar liquid displays a convex meniscus. Okay, a non-polar liquid. See this? A non-polar liquid displays a convex meniscus, like that. Which of the following explains this behavior? This relates to our discussion of cohesive versus adhesive forces. Cohesive forces tend to are those that the substance attracts to one another inside in the material. Adhesive forces are between the material and its container. So which ones win in this case? When you see a meniscus like that, that means that the internal forces, the cohesive forces, are stronger than the adhesive forces. If it was the other way around, your meniscus would be that way. That one's giving out on me. I hope this one's working now. Okay, so to answer that question, we look for cohesive forces are stronger than adhesive forces. That's true. Now, the problem with this question is cohesive forces are stronger than adhesive forces to the glass. There's no mention in the question of glass. It just says in a container. Right? So the answer gives us more information. All right. So let's move on to, my goodness, number 9. Which substance can be described as cations bonded together by mobile electrons? Okay, I'm not sure if we hit on this one very hard in the lecture part of the course. But what they're describing here is a visualization of how metals bind together. Yeah, that was 9. So with metals, what we're looking at is there's the metal atoms, right? And these atoms, absent their electrons, would be positively charged, correct? Well, we've got electrons here that are very mobile. And what they're doing is they're providing a bonding force for neighboring atoms by way of these electrons. So these are attracted to that electron, these to that one to that one, positive and negative attractions. So what we do to answer that question is look at our selections and see, are there any metals there? And in fact, there are. Silver would answer that question. Sulfur does not. It's not a metal. And in fact, S8 is a covalently bound allotrope of sulfur. Krypton, that's a noble gas. It has no mobile electrons. KCl, that's ionic bonding. And HCl is hydrogen bonding, and maybe let's just say dipole interactions. Okay, so the best answer based on this statement here is silver. How about 10? Which of the following statements about steel is false? Okay, think about steel. What is steel? Well, it's a homogeneous mixture of iron and some other stuff. It at least has carbon in it. It could have some other things, but it definitely has carbon. Okay, so which of the following statements about steel is false? We're looking for the false one.
Give him that baby. Adam. The hammer.
Oh, really? A, it contains carbon atoms in the holes of its iron crystals. That's true. This is what's known as an interstitial alloy. The carbon atoms are very small, the iron atoms are big, but they don't take up all the space. There are voids in there, and the carbon atoms occupy those voids. So A is true. The presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. That is also true. From an engineering standpoint, those crystals of iron, normally pure iron is very malleable. They can slide past one another. You can scratch pure iron with your fingernail. But when carbon is added, it fits in those spaces and it bonds with the various iron atoms and locks those crystals in place. So the more carbon you have, the harder the metal. In fact, if you have too much carbon, you can make it very brittle. It might be very hard as far as wear goes. In other words, you could put high carbon steel as a cylinder in your engine and it would wear forever. The pistons will wear out before the cylinder would. But you'd have to give it lots of support because it's very brittle. All it takes is just a strike in the wrong direction and that thing would shatter. So there's a happy medium in there for wear resistance versus durability. But B is true. That is a true statement. C, pure iron is relatively soft and ductile because it lacks directional bonding. That is also true. Remember when we described metals? It's like cations in a sea of electrons. So they're free to move. They're bonded together, but they're still free. We can push them around. That's non-directional bonding. That's true. D, the amount of carbon directly affects the properties of steel. Well, I described that to you also. The amount of carbon. Anything above, let me scratch my head for a minute. 0.5% carbon by mass is considered high carbon steel. Actually, 0.3% would be high carbon steel. Low carbon steel would be in the neighborhood of 0.2 to 0.1%. So how do sword makers get around that? Well, they add other stuff to it now. And it's a different kind of alloy that allows you to make steel that's both strong and resilient. So your sword won't break. It'll still cut, but it won't break. Now, the ancient sword makers, like the Japanese, who made their katanas, would laminate different grades of steel in their blades. And what they would do is they would put the softer, more resilient steel on the inside and clad it with higher carbon steel, which made for a good cutting edge, but it had that support from the back, from the internal soft steel. And then the way they treated it, they would heat it up, and then when you quench it, if you quench it quickly, then it locks those crystals into place and hardens the edge. But before they did that, excuse me, I left something out. They would coat their blades with a special clay. They would dab it up and down the blade and let it dry and heat it up and then quench it. And the thin edge would quench quicker, which made it harder. And the clay would insulate the back of the blade and keep it softer. So it'd give that flexibility and strength. And then the cutting edge would be much harder. So that's how they got around these problems with the different carbon content. Okay, that's enough of that. So the answer is E. All of these statements are true. 11. Which of the following statements is true about P-type silicon? What do they mean by P-type silicon? Well, if you've got silicon, pure silicon, as the base element of your semiconductor, it has so many valence electrons. It has 4 valence electrons. Okay. If you dope it with an element to the right of it in the periodic table, right? Like here's silicon. If you dope it with phosphorus, phosphorus has 1 extra electron. Phosphorus has 5 valence electrons. So when you make an alloy with that, you dope it with phosphorus, you're adding an extra electron. That makes it an N-type silicon. This alloy would be N-type. So a P-type would be something to the left of silicon in the periodic table. Like, let's say, boron. Boron has only 3 valence electrons. Right? So when you dope this one, you're short in various places inside that alloy. You're short 1 electron, which makes a P-type, standing for positive. Okay. So now that we've reviewed that, a P-type silicon, it is produced by doping silicon with phosphorus or arsenic. Well, no, phosphorus and arsenic are both to the right. It makes an N-type. So A is false. How about B? Protons are the mobile charge carriers. Can that be true? No. Protons are the backbone of the alloy. They are locked in place. The only thing that can move is electrons. So if you have an N-type, then those extra electrons can move. If you have a P-type, then it's said that the holes move. The missing hole, the holes where you're missing an electron move. Actually, what happens is an electron moves to fill one hole and leaves the hole behind. So the electron moves one way, and it looks like the holes move in the other direction. So protons are not the charge carriers. It does not conduct electricity as well as pure silicon. That's false. Silicon is a good insulator. But once you produce this unbalance in the charge, now you have the ability to move charges. These are semiconductors. So none are true. All three of these statements are false. All right, let's see, what's my next one I got marked off. Let's go down to 14. A solid crystal of sodium chloride is what? All right. It looks like we're characterizing physical properties of sodium chloride. All right, what does the crystal of sodium chloride look like? It's solid, and it's composed of cations and anions. So you're going to have a sodium, and it's surrounded by plus there's a chlorine behind and there's a chlorine in front. But when you're focused on the chlorines, what do you have? You have sodium. With a sodium in front and a sodium in back. Okay, so each one of these is surrounded by 6 neighbors. Right? Sodium plus is surrounded by 6 chloride, and chloride is surrounded by 6 sodiums. Okay, so the ratio is actually Na6Cl6, but the simplest ratio is NaCl. All right, what does that mean? Well, first of all, these are very strong bonds, right? We're going to have very high melting point, and it's going to be hard because when you try to push on it, these things are locked in place. They're not going to move. So we're looking for something that's hard, B or D, and high melting, B or D. Right? So now the question is, what's the third characteristic that we're trying to impose upon this crystal? Is it a good electrical conductor or a poor electrical conductor? Well, what does that mean? Something that conducts electricity is able to transmit charge, a current, from one side to the other. So, do we have any mobile ions here that can do that job for us? No. They're locked in place. They're in that crystal structure to stay. The only way you can get them to move, actually, there are 2 ways. Either melt your sodium chloride, which frees up the ions to move, now they conduct, or throw some in water, and the water will do the breaking for you. It'll just bust up the ions, sodium chloride, now they can conduct electricity. So this solid crystal of sodium chloride is an electrical insulator. It's a poor electrical conductor. That's why D is the answer. All right, let's see. Let's move down to, well, I got a series of them here. 15. Which of the following has the highest melting temperature? 15. Well, let's see what we got. Right? What are the forces? What are the forces that are responsible for determining melting point? Well, we've got ionic bonding, we've got dipole-dipole, or actually dipole-ion interactions, whatever the case may be, and then we have London dispersion forces, strongest, next, weakest. So let's look at what we got. Water is hydrogen bonding, dipole-dipole. So that should have moderately high. melting point. Carbon dioxide. No, carbon dioxide is a nonpolar molecule. So it's looking at van der Waals. Sulfur is nonpolar. But yeah, that's true. That's true. It's nonpolar. So if we're looking for the highest melting point, we're looking for the thing with the strongest intermolecular forces. And actually, that stretch that definition, because when we talk about ionic compounds, you don't have molecules, right? But the highest melting temperature will be the ionic bonding, and that is magnesium fluoride. Magnesium fluoride makes a pretty crystal. It's transparent. I used to work with an instrument that had a lens in it, special kind of lens. And it had to be a lens that would transmit ultraviolet and focus ultraviolet radiation. Because of the nature of the instrument, I needed to be able to detect ultraviolet radiation. So we couldn't use quartz glass, right, which would have been much more durable, but it would absorb ultraviolet. So we had to use magnesium fluoride as our lens. You had to be careful with it, because it was easier to scratch magnesium fluoride than it would be quartz. But it has an extremely high melting point. So that's really a no-brainer. 16. Which of these statements is false? Diamond is a covalent crystal. That's true. Every carbon in the diamond network, it's a network solid, is covalently bound to the other one. That's true. How about B? The size of the unit cell of lithium and cesium is the same. Think about it. Lithium is a very small atom. And cesium is a very big atom. They're in the same family. Lithium and cesium. So when you form your unit cell, in fact, it really doesn't matter which unit cell you form. They're probably going to form similar, not guaranteed, but possibly. But you need more space for the cesium to form the unit cell. So based on that alone, I would say this statement is false. The size of the unit cell, even if it's the same type of unit cell, has to be bigger for cesium. We found our answer. That's the false one. None of the statements are false. Well, that can't be right, because we found a false one. C, molecular crystals usually have low melting points. Yeah. Molecular crystals, that is individual molecules bound together. So what do they have available to them? They don't have ionic bonding, right? They've only got either dipole-dipole or van der Waals. So they tend to have low melting points. Metallic crystals are usually good electrical conductors. That's false too. No, that's true. Excuse me. Metallic crystals, the metal with that sea of electrons, those are good conductors. Electrical conductors and thermal conductors as well. So D is true, C is true, A is true, B is false. Uh, 17, yes. All right. How would you expect the melting point of carbon tetrachloride to compare to that of sodium chloride? Well, that's pretty simple. Sodium chloride is an ionic compound. And carbon tetrachloride is a non-polar molecule. So the bonds between the individual molecules of carbon tetrachloride are going to be much weaker than between the ions of sodium and chlorine. So what do we say? The melting point, that's what they're saying. The melting point should be lower for carbon tetrachloride because sodium chloride forms an extended ionic crystal lattice, where carbon tetrachloride is covalently bonded small molecule. That's true. That's your answer. And I don't see any other oddballs in here. They're not both ionic solids. Carbon tetrachloride should be higher because the bonds are stronger due to the higher charge. I don't think so. That's pretty made up there, I think. Should be higher because carbon tetrachloride is larger than sodium chloride. Well, that may be true, but that would only be an answer to the question if you were comparing two covalent compounds. Okay? If you had, that's a good example. How about this one? Versus, right? These are both nonpolar, right? Tetrahedral structure for carbon tetrachloride and methane. This one has a higher melting point because it's a larger molecule. So now we have London dispersion forces on a larger molecule that can be much greater than they are for a smaller molecule. Now that would be true. This statement D would be true if instead of sodium chloride, we said methane. Okay, it's not possible to say anything about their melting points. Well, that's false. We can say plenty about their melting points. How about 18? Yep, 18. Which of the following is most likely to be a solid at room temperature? Well, in this case, we want the one with a strong intermolecular force, something that holds it together. And the easiest approach to this one is look for any ionic solids. If you've got ionic solid here, then you got a solid at room temperature. No doubt about it. Sodium sulfide is an ionic solid. It's going to be solid at room temperature. HF, no. Ammonia, no. Nitrogen, no. Water, no. So that's really a no-brainer. 19. At normal atmospheric pressure and a temperature of 0 degrees Celsius, which phase of water can exist? All right. So what are we talking about here? For water. At 1 atmosphere pressure, 0 degrees Celsius. What is that? That's the freezing point of water. What do we know about the freezing point of water? We know that at the freezing point, you can have both liquid and solid together at the same time. If we look at the phase diagram for water, pressure, temperature. All right, so if we go here to that point, this is gas. This is liquid, and this is solid. So at 1 atmosphere, and I'm not sure where that would be. I think probably up in here somewhere. If we have a solid and a liquid at 0 degrees, right here in 1 atmosphere. On that line, you can have solid and liquid at the same time. That's what that phase line means. So the answer is ice and water can exist at the same time at that temperature and pressure. At this temperature and pressure, you can have solid and gas. At this pressure and temperature, you can have liquid and gas, right? If that's still 1 atmosphere, that will be at 100 degrees Celsius. All right. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? All right. A reminder of what these terms stand for. All right. If we have a liquid here, let's say a liquid, solid, and gas. Okay, we can have phase changes among all 3 of those. So if we go from liquid to gas, that's called evaporation. And if we go from gas to liquid, that's called condensation. Okay. Well, liquid to gas, we could say that's boiling also. Okay. If we go from liquid to solid, let's go from solid to liquid. That's melting. And if we go from liquid to solid, that's freezing. And if we go from solid to gas, that's sublimation. And if we go from gas to solid, that's called deposition. Okay. Now that we've got things organized, let's see what the answer is. Which of the following processes must exist in equilibrium with evaporation when a measurement of vapor pressure is made? So what's going on when vapor pressure is being exhibited above a liquid? If you've got a container here, you got a liquid down here, right? And you got the gas up here, what's happening? Well, you've got molecules going this way, and you've got molecules going that way, backwards and forwards. So liquid to gas, is evaporation or boiling. And gas to liquid is condensation. So equilibrium, which is in equilibrium with evaporation? Evaporation, condensation. Okay, that's why E is the answer. It's the opposite of evaporation. All right. All right, got a lot of them in this one. 21. All right, 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? The highest vapor pressure would be the one with the weakest intermolecular forces. So it would have the lowest boiling point. Okay? So you look for the lowest boiling point. 100, 64, 78, 34. There you go. Diethyl ether will have the highest vapor pressure. 22. Which of the following decreases as the strength of the attractive intermolecular force increases? If you increase the force, oh, it's the one we just discussed. Remember, all of the other measures of any type of matter, whether it's boiling point, freezing point, sublimation temperature, vapor pressure. Everything but vapor pressure increases its value, its measured value, as the intermolecular forces increase. As you increase the intermolecular forces, well, I erased my drawing, then the liquid expels fewer molecules into the gas phase. So it's just the opposite then. Increase the forces, decrease the vapor pressure. So the vapor pressure of the liquid would decrease as the attractive forces increase. 23. In which of the following processes will energy be evolved as heat? Okay. So if we're going to be exothermic, okay, let's look at it in terms of our system surroundings. System surroundings. So an exothermic process will evolve energy, right? So heat's going to go this way. So what's happening in the system if heat is leaving? Well, the system is becoming less energetic. So what does that mean in terms of phase changes, right? That's what all these things are, phase change. The phase change has to go from a higher energy state to a lower energy state. So I'm talking about gas to liquid, liquid to solid, or gas to solid for heat to be evolved. So sublimation goes the other way. It goes from solid to gas. Crystallization, okay? It goes from, well, that's not one that's mentioned in our triangle, but crystallization takes individual particles and brings them together, bonds them together. When that happens, they make a lower energy state product, which means that energy has to go somewhere and it goes out, exothermic. So crystallization answers the question. Vaporization goes from a liquid to a gas, you got to put energy in. Melting goes from a solid to a liquid, got to put energy in. So crystallization would answer that question. (24) The normal boiling point of liquid X is less than that of Y. The normal boiling point of X is less than the boiling point of Y, okay? Which is less than Z, okay? All right. Which of the following is the correct order of increasing vapor pressure of the free liquids? So if this boiling point is higher than that one, that means the intermolecular forces here are greater. And the intermolecular forces here are greater. So the vapor pressure is going to be highest for this one. So the vapor pressure of X should be greater than vapor pressure of Y greater than vapor pressure of Z. It's just the opposite. So it says correct order of increasing vapor pressure, right? That to that to that. So ZYX would be increasing vapor pressure. ZYX. Okay. 25. Let's see. Let me shrink it just a little bit. There we go. Okay, choose the correct statement about the diagram below. So what are we looking at? We're looking at a phase change diagram, a phase diagram of some compound or some element where you have solid here, liquid there, gas there, just like I drew before. And it's giving you the temperature scale is on the x-axis, pressure is on the y-axis, and 1 atmosphere line is right there. Okay, that's given. Which is the correct statement? The diagram is qualitatively correct for water. Is that true? No. The solid liquid phase line should have a slope tilted back the other way, right? Most substances exhibit this type with a slope to the right, a positive slope. Water has a negative slope for solid liquid, right? So it can't be water. The diagram shows that the melting point of the solid increases with increasing pressure. So where's the melting point? Solid, liquid. Right. So as we increase the pressure, what happens to the melting point? Yes, it does increase, right? This is a positive slope. Increase the pressure, you increase the temperature. So B is true. E says none of the above statements is correct, so it can't be E. We found a true one, B. Well, that's the correct statement. The diagram shows the triple point above 1 atmosphere. Now it's below 1 atmosphere. Here's the triple point right there. So it's below 1 atmosphere. The diagram could represent the phase diagram of CO2. Well, is that possible? What do we know about carbon dioxide? Well, carbon dioxide, if you take solid carbon dioxide and set it on the benchtop, what'll it do? It'll go straight to gas. So at 1 atmosphere pressure, we should be able to go straight from solid to gas. In other words, we should be able to go like that, solid to gas. It can't happen. At 1 atmosphere, this substance goes from solid to liquid to gas. Right? Can't be carbon dioxide. So the answer is B. Uh, 26. Oh, another phase diagram. Let's see. Yep, we got everything in frame. Below is a phase diagram for compound Q. Right? It doesn't tell us solid, liquid, gas. So we have to assume that this space over here is solid, this space is liquid, and this space is gas. Okay. You wish to purify a sample of Q that was collected at 1 atmosphere, 1 atmosphere and 100 K. So it was collected, it was collected right about here. 1 atmosphere pressure and 100 K. And you want to sublime it. In order to sublime the sample, you should do what? If your starting point is here, then how do you sublime? You got to go from solid to gas. So you got to decrease the pressure and then increase the temperature. So increasing the pressure won't do it. Increasing the temperature, keeping the pressure at 1 atmosphere, won't do it, because that'll take it through liquid. So you got to lower the pressure. Is this one correct? Lower the pressure to a 1/2 atmosphere and then increase the temperature to 200. That would do it. That would put it right over here. So C would answer. Yeah, C would be the best answer. Abandon the attempt. No, I don't think so. We can do that. 26 is C. All righty. How about, oh, good. We get to skip over to 29. Yep, got everything in frame. 29. Okay, given this phase diagram, which of the following statements, A through D, is false? All right, what do we have here? Let's see. We got a negative slope on our solid to liquid phase line. And we got temperature, and then we got this over here identified as A. I think X is the position and A is the identifier for the data point, X. Okay, which is false. The solid has a higher density than the liquid. The solid has a higher density than the liquid. Solid. Okay, here's the solid, and there's the liquid. I'm not sure how to answer that one. Okay, I see what it's getting at here. This may or may not be water, but even if it is, it's not water. It exhibits a similar behavior to water. So what does that say? Well, we know that the solid water or ice is less dense than the liquid, right? And since this one has a negative slope here between the solid and liquid, then we may infer that this substance has a lower density solid than the liquid. So A would be false. All right, so that answers the question. Either that, or we look at all the others and find that they're true. But then again, we can't say that none of the above is false, because then if we assume that A is true, then E would be the answer. So you have to actually infer from the phase diagram similarity to that of water that the solid has a lesser density than the liquid. Right. That's kind of a tricky question there. Okay, 30. The measure of resistance to flow of a liquid. This is just memory. What's the resistance to flow of a liquid? It's called viscosity. All righty. How about, oh, that was the easy sections. Let's move into the moderate section. Here we go. Which of the following, let's see, I got something in the way here. Which of the following is the correct order of boiling points for KNO3, CH, methanol, C2H6 is ethane, and neon? So it looks like they're all going from left to right, increasing boiling point from left to right. The lowest boiling point is going to be that noble gas, because all it has is London dispersion forces available to it. So it's either A, C, or D. The highest one would be the ionic solid, KNO3. So if we got neon and KNO3, it could be A or it could be D. So now we have to say, all right, C2H6 and CH3OH. We have to see what order are these guys in. The higher boiling point is going to be the one with the higher intermolecular forces. Right? C2H6 is nonpolar. Right? It's like this. Right? Whereas CH3OH has hydrogen bonding, right? So it's going to be closer to potassium nitrate than ethane. So that's why D is the best answer for this one. Let's see, 2. Which of the following statements are false? All right. Layering in a hexagonal closest packing structure is ABA. Hexagonal closest packing. Well, you have to remember the relationship of hexagonal closest packing to the this just memory. And when we looked at the let's see, when we were introduced to this topic, there was a correlation, actually an identity, drawn between hexagonal closest packing and ABA, and they are the same. So that's just memory. A body-centered cubic unit cell has 4 atoms per unit cell. You can derive this one. So Roman numeral 2, a body-centered cubic unit cell. A body-centered. So you got 1 in the middle here, and then you got here, 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 and here. Okay, body-centered cubic cell. How many atoms are in this unit cell? Well, this one belongs to the unit cell, so that's 1. How many of each one of these belong? 1/8 of the corners belong to that cell. So we got 1, 2, 3, 4, 5, 6, 7, 8, plus 8 times 1/8 equals 2. So the number 2, this one's false. It's not 4 atoms per unit cell. It's only 2 for a body-centered cube. Okay, so we know that one's false. So it's either B, C, or E. So let's see what Roman numeral 3 has to say. For unit cells having the same edge length, a simple cubic structure would have a smaller density than a body-centered cube. Right? What is it that determines density? It's mass per volume. So how much volume, if the edge length on a cube is the same, that means the unit cell has the same volume. So a simple cubic cell only has mass at the corners. Right? So mass divided by volume is a certain value. But if you stick another mass in the center, you increase the mass for the same volume. So the density of the body-centered cube is greater than the simple cube. The simple cube has a smaller density than the body-centered. That's true. How about 4? Well, let's see. 3 is true. So it can't be C. Well, it can't be E, right? So it has to be B. And we could look at 4. Atoms in a solid consisting of only one element would have 6 nearest neighbors if the crystal structure were a simple cubic array. Well, yeah, that's true. Simple cubic. So here, how many neighbors do you have? Well, you've got one here. You got one here. You got one here. Then you've got one over here with a neighbor there. One over here with a neighbor here. And then one down here with a neighbor there. So you have 6 neighbors. Number 4 is, Roman numeral 4 is true also. About 3. And a good example of that simple cube with 6 neighbors is sodium chloride. 3, which of the following substances would you expect to have the lowest boiling point? Lowest boiling point. Okay. Weakest forces between molecules. Right. Copper is going to have a pretty high boiling point. It's a metallic, non-directional. Glycerin or glycerol has hydrogen bonding. Right. Sodium nitrate has ionic bonding. Diamond is a network solid. Right? If you try to boil diamond, you're probably going to decompose it before you get to the boiling point. Methane, right? That's a nonpolar gas, which would have the lowest boiling point because the only intermolecular forces it has at its disposal are the London dispersion forces. All righty. So number 4. Okay. This might take some calculation here. Well, I should say medium 4. Assume that 12,500 joules of energy is added to 2 moles of water as an ice sample at 0 degrees. Molar heat of fusion is that number. Specific heat of liquid water is 4.18. The molar heat of vaporization is 40 kilojoules per mole. Resulting sample contains what? Only ice, ice and water, only water, water and water vapor, only water vapor. So what they're looking at is a phase, this type of phase diagram. So we've got the temperature here, and this is progress. So as the temperature goes up from here to here, what you have is melting. So this is, well, actually, this is not melting. This is the solid. This is the solid and liquid melting, right? This is the liquid only. And then this is the liquid and gas. And then this is the gas only. So it takes a certain amount of heat to go up to here, and then a certain amount of heat to melt everything, and then a certain amount of heat to increase the water temperature, right? We're talking about water? Yeah. And then here, we're boiling the water. It takes a certain amount of heat there, and then heat for gas, okay? We have only 12,500 joules at our disposal. Okay. So where are we starting? Water as an ice sample. An ice sample. Here. At 0 degrees. So we're right here. Right there. At 0 degrees C. Right. So we're not going to heat the ice up. The ice is already at 0 degrees. Now we're going to melt it first. Right. So you need to remember how to calculate the heat required to melt. So look at what we've got. The molar heat of fusion. That's how much energy it takes to melt the ice. 6.02 kilojoules per mole. Right? So the heat of fusion is equal to 2 moles of water times the molar heat of fusion, which is 6.02 kilojoules per mole. All right, so that's equal to 12.02 kilojoules. All right, and we've got 12.5 kilojoules, right? 12,500 joules. So we've got 12.5. Let's do it the other way. Let's change this to joules. 12,500 joules is your starting point, and we're subtracting 12,020 joules. So now we got 0.84. 480 joules left. Okay. All right. So the next, that gets us to this point right here. Now we're going to heat the water up. Do we have enough energy to heat the water from 0 to 100 degrees? Well, what's the relationship here? Oops. That's a 6. There we go. 460. Remember the specific heat of water and the formula. Right? Delta H equals, or Q that we called it earlier, is the specific heat times the mass times the change in temperature. Right? Specific heat is 4.18. What's the mass? 36 grams. What's the change in temperature? Well, we know the starting temperature is 0, and the ending temperature is something. So this is going to be equal to how much energy we have left, 460. So if we solve for that final temperature, what is the final temperature? If we do all that math, final temperature is 3.06 degrees C. We're still liquid. Liquid only. Okay? That's why the answer is C. Only the liquid. Right? We haven't put in enough energy to go any higher. We don't have enough energy to do it. All right. So next, we dip into the difficult section. Let's look at this one. Here we go. All right. So we're going to do difficult 1. let's see, a crystal was analyzed with X-rays. Having 2.33 angstrom wavelength. The angle of first order diffraction, n equals 1, was 19.2 degrees. What would be the angle for the second order diffraction? Right. This problem is Bragg's. This needs Bragg's equation. Right? And Bragg's equation is n times the wavelength equals 2 times the distance between the lattice layers times the sine of theta. So we can approach this two different ways. Let me think for a second. It'd probably make more sense if we solve it 2 steps. So what we need to know in order to solve this equation for the new angle, the distance is going to be the same, right, for the same crystal. The wavelength of the light shined on the crystal is the same. The n is going to change. So when the n changes, it changes the angle. All right. So if we put in the information we know, 2.33 angstroms. Let's see. Can I do that? Yes. And 1 here equals 2 times d sine of 19.2 degrees. Okay. Now we solve for d. So we say d equals 2.33 divided by 2 times sine of 19.2. So when we solve that equation for d, we get 3.54 angstroms. Okay. Now for the next equation, instead of 1, we're going to have 2 here. So 2 times the same wavelength of light equals 2 times 3.54 angstroms times sine theta, the second order theta. Then we just put everything on this side, and then, well, let's do that. Let's see, 0.658. So if I take this number, divide it into that one, 0.658. Yeah, 658 equals the sine of theta. Now, how do you solve that? Well, this theta is going to be the arc sine. The arc sine of 0.658. That's what it will look like on your calculator. Arc sine. Let me see. On mine, you look for the sine, and then above it, mine has a sin, arc sine. Right. So I would put 0.658 in, and then I would do the function for arc sine, and I get 41.1 degrees. Close enough. And this marker's not working too well. I might have to throw it out and get another one. That's a little better. Okay, so the answer is, the nearest answer is 41.1 here. All right, that would be the second order angle. Okay. 2. Yeah, 2. Chromium metal crystallizes as a body-centered cubic lattice. So we've got chromium, solid, and it's a body-centered cubic lattice. If the atomic radius of chromium is 1.25 angstroms, so R equals 1.25 angstroms, what's the density of chromium in grams per cubic centimeter? So we're looking for density in grams per cubic centimeter. Right? That looks like an insurmountable problem. But look at it this way. Let's work backwards. Density is equal to mass per unit volume, correct? So those are the values we need. The mass that's associated with the volume. So what we need is the mass contained within that cubic lattice. And the volume is determined by the radius of the atom, right? We have a formula for that, body-centered cubic. Let's see, I think it's in useful information. BCC, the edge of our cube is equal to yes, the edge of the cube is equal to 4r divided by the square root of 3. So the edge of our cube here that edge is equal to 4r divided by the square root of 3. Right? And this r is that r right there. Okay? So what's the volume of that cube? The volume of the cube is a cubed. So we would take r and put it in here. Well, the volume is equal to a cubed, which is equal to 1.25 angstroms divided by square root of 3, and that is cubed. That's the volume in angstroms. But we need it in cubic centimeters. So let's see. In the interest of time, let me see. Where is it? Volume is a cubed. Convert. Oh, okay. So the way I worked the problem here, I calculated A first and then converted to centimeters, which is probably a better idea. Let's do it that way. Like that. Okay, so that's going to be 2.887 angstroms. And then we'll convert angstroms to centimeters, and then we'll cube it. So, how many centimeters in an angstrom? Well, an angstrom is 10 to the minus 10th meters. Right? An angstrom equals 10 to the minus 10th meters. So if we take 100th of that for centimeters, it would be equal to 10 to the minus 8th centimeters. Okay? So now we have an equivalence. Put this on the top. Put this one on the bottom. They cancel. Now we have the edge of the cube is 2.887 times 10 to the minus 8 centimeters. Then we want to cube that to get our volume. And the volume there is 2.406 times 10 to the minus 23rd cubic centimeters per unit cell. Okay, now we have our volume. Let's see, I'm gonna have to erase some of this here. So this is 2.406 times 10 to the minus 23rd cubic centimeters per cell. Now we need the mass. We need the mass of chromium in that cell. Well, we determined earlier that how many atoms are in that unit cell. Now, body-centered cube, there are 2 atoms in there. 2 atoms of chromium. Okay, so if we've got 2 atoms of chromium per cell, we want to know what's the mass in that cell. Okay, what we need is molar mass. So how many moles does 2 atoms represent? 6.022 times 10 to the 23rd atoms per mole. Okay. Now we can get mass per mole. Chromium. Let's look up chromium here. Let's see. I'm looking at my periodic table. 51.996. 51.9961 per mole. Mole's gone, mole's gone. So now we got grams per unit cell. And that will be 1.727 times 10 to the minus 22. Okay, so we put that up here. 1.727 times 10 to the minus 22 grams. And all you have to do is now calculate that value, which is 7.18 grams per cubic centimeter. And there it is. Right there. Okay. That was a lot of work, I know. But we did get the answer. Let's see. That was 10. Got any more in here? Oh, no, that wasn't 10. That was 2. Yeah, that's it for chapter 10. And we're up to 3 o'clock. It took 2 hours to do 1 chapter. Okay. Let's see if we can go any quicker on chapter 11. So I have to stop this share and share, where is it? Here it is. And share the other one, chapter 11. Okay. All right. Here we go. Chapter 11. This is going to be, easy, medium, hard. So easy one. Okay. In a 0.1 molar solution of sodium chloride in water, which one of the following will be closest to 0.1? What do we mean by 0.1 molar? 0.1 moles per liter. Okay. We could go in and calculate each one of these, which is what I did for the worked problems. But what we're going to find is that this is moles of sodium chloride. And the only difference between molar and molal is this value. 0.1 moles of sodium chloride is going to weigh almost nothing. So we're really looking at the relationship of volume to mass. So molal is actually kilograms. This is solution, and this is solvent. So that's why I said the relationship here is not dependent so much on the amount of sodium chloride, but on the relationship of volume to mass of the solvent. And in this case, it's water. So 1 liter equals 1 kilogram. So what we're saying here is this is almost exactly 1 mole of sodium chloride per kilogram of solvent. It's not exact. Let's see, I actually did the calculation. Molality is a little bit less than this because let's see. No, it should be greater. It should be greater because here it's liter of solution. Here it's kilogram of solvent. So we have a little bit less mass here, plus the density of water is not exactly 1. It's a little bit less than 1. So this should be a little bit bigger than that and make this actually a little bit greater than 0.1. But it's very close. That's why I'm saying that, and it's not all of these are 0.1. And that's because of the actual calculation that goes into the, let's see. The first one is mole fraction is 0.0018. The second one is mass fraction, 0.00586. C is mass percent, 0.586%. And D is molality, which is 0.1006. So if we do all the calculations, we find that molality is the nearest to 0.1 of any of those. How about 2? Which of the following concentration measures will change in value as the temperature of a solution changes? Okay. All we need to know is what factors, what physical factors determine these concentration units, right? And are any of those factors susceptible to change with temperature? Mass percent. Mass doesn't change with temperature. It's the amount of a substance. Mole fraction. The numbers of particles does not change with temperature. The number of moles does not change. Molality is based upon moles, numbers of things, and mass. So it doesn't change. Molarity is moles per unit volume, and volume does change with temperature. So D is the answer to this question. 3. Which of the following chemical or physical changes is an endothermic process? Endothermic. Energy goes in. So let's see what kind of changes we're talking about. Evaporate water? Yeah. If you're going from liquid to a gas, you've got to add energy to break those bonds and make a gas out of a liquid, right? Well, E says none of these. We found one that was true, that one. So that's it. Combustion of gas is exothermic. That's obvious. Mixing of sulfuric acid and water. Anytime you combine a concentrated acid or a concentrated base with water, if it goes into solution, it will get hot. That's why we say, do as you oughta, add acid to water. If you add a little bit of acid to a lot of water, then you're less likely to boil it and spatter. But if you add water to acid, then it's going to go into solution, produce enough heat to boil that water, and it'll spatter right back up in your face. Okay, the freezing of water. As water freezes, the molecules get closer together, lower energy, they give off energy. So freezing water is an exothermic process. A is the answer to 3. 4, which statement about hydrogen bonding is true? Hydrogen bonding is the intermolecular attractive force between two hydrogen atoms. I don't think so. The hydrogen bonding capabilities of water molecules cause this non-polar molecule to be more soluble in water than CH3OH. So the way around. Methanol is much more soluble than butane. Hydrogen bonding of solvent molecules with a solute. Solvent with solute hydrogen bonding will not affect the solubility. I beg to differ. Hydrogen bonding enhances solubility, if there is any. Hydrogen bonding interactions between molecules are stronger than the covalent bonds. No. That was one of the first things we learned. Intramolecular bonding is much stronger than intermolecular bonding. Otherwise, the molecules will be ripped apart by those extramolecular forces. D is false. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. Yeah, that's true. It's not just certain. Covalent bonds. It's bonds between certain atoms and hydrogen. So it's true, but a little incomplete. 5. Which of the following favors the solubility of an ionic solid in a liquid solvent? An ionic solid in a liquid solvent. What favors them? A large magnitude of solvation energy of the ions. if you have to put a lot of energy, let's see, a large magnitude of the solvation energy. Yeah, you have to put a lot of energy into the system to make it go into solution. That's not going to favor solution. The small magnitude of the lattice energy of the solute. Okay. Let me get my wording correctly here. Remember that chart where we had a three-part, let's see, this one is 5. Right. Dissolution is a 3-part process. Part number 1. Break solute apart. This is endothermic. 2, break solvent apart. Make a hole. This is endothermic. And 3, form solute solvent bonds. This is exothermic. All right. So what favors the formation of a solution? When you put in energy here and you get energy back here, and they're roughly equal to one another. These two are roughly equal to that one. You favor the formation of a solution. When you put a lot of energy in here and you get a little bit back, that is unfavorable. Or if you only put a little bit of energy here and you get nothing, and you get, let's see, and you get a lot of energy back here, that also favors not forming a solution. So it's when they're roughly equal, 1, 2 equals 3. So if we go back and look at our choices, which of the following favors the solubility of an ionic solid in a liquid solvent? Well, let's see. A large magnitude of the solvation energy of the ions. Solvation energy, large magnitude. Now we're talking about ionic solid in a liquid solvent. So these are not simply by themselves. A large magnitude of solvation energy of the ions. So once you get the ions separated, do you get energy back? Well, yeah, okay, that's good. A small magnitude of lattice energy of the solute. So the lattice energy of the solute is this one. Lattice energy is going from individual ions in the gas state to a solid. The small magnitude of lattice energy. Small magnitude of lattice energy means it takes only a little bit of energy to get them apart. And a large polarity of the solvent. The large polarity of the solvent means it takes energy to get this apart. You know, that doesn't make any sense. That's probably why I referenced this this table. All right. If you put in a lot of energy here, a lot of energy here, and you get it back, that favors the formation of a solution. That's a bad question, I think. let's move on. Okay. 6. Solid KF has a lattice energy of minus 804 kilojoules and a heat of solution of minus 15 kilojoules per mole. Rubidium fluoride has a lattice energy of minus 768 and a heat of solution in water of minus 24. Which salt forms stronger attractions with water? Okay. Stay with me here. 6. So we really have to define what do we mean by lattice energy and heat of solution. Well, if we look at the heat of solution, let's see, the 6, heat of solution is divided into those 3 parts. So the first part is, let's see, delta H1, delta H2, and delta H3. This is the one where you break apart the solid into its individual parts. And this is the lattice energy. That's the lattice energy. The second one is called solvent expansion. This one is solvent expansion. Right. So we put energy in here, we put energy in there. And the third one is solvation. So that's the energy we get back. Okay. These two combined, we can call the heat of hydration. The reason we can do that is because the both are dissolved in water. So the solvent expansion is going to be equal for both cases. And they're really due to this value right here. And the question here, which salt forms stronger attractions with water? Well, this heat is due to that one. So the stronger attractions here can also be translated into that one because this one is constant. Right? So that simplifies the situation. If we know this one and that one, then we can calculate that one. Okay, so that's what we're going to do next. The lattice energy is, we're going from individual ions. Let's see, how do I put that? The lattice energy is the energy you get back, positive, when the gas ions condense into a solid. You get energy back. But for this, we're putting energy in. So the value that we put in here, we need to use a negative sign. We have to change the sign because we're actually going the other direction. We're breaking it apart, not pulling it together. So that's why this one needs to be a negative. Okay, so the heat of solution is equal to the negative lattice energy plus the heat of hydration. Okay. Now, the values that were given, the lattice energy is, KF is minus 804. So here's KF minus 804 here. minus a minus 804 plus the delta H for Kf. That one. And that's equal to the heat of solution for Kf as minus 15. So this is minus 15. Are they all kilojoules? Yeah, okay, well, apples and apples. Okay, so, and rubidium fluoride is minus 24 equals minus 768 plus delta H rubidium fluoride. Okay, so we're solving for this one for each one of those. Now, if we solve Kf is minus 819, right? Because this is positive, then this one is minus 819 kilojoules. And this one is minus 792. Okay. So this heat of hydration, the larger negative number, as things come together, a larger negative means a stronger attraction because it's an exothermic process. Well, I erased it, but it's exothermic. So this larger value means that the salt, the Kf, has a stronger attraction with water than does rubidium fluoride. So Kf is a stronger attraction since it has a more negative heat of hydration. That is the answer to this one. All right. Moving along. Yeah, it's going to have 7 too. Let's see. I can't get everything on there. So let's read the question first. Use the following drawing of a gaseous solute. In equilibrium with a solution to help answer the question. So what do we have here? We've got a gaseous solute. So we're dissolving a gas into a liquid. It's not vapor pressure. This is Henry's law. And Henry's law is, let's see, number 7. Henry's law is the concentration of that gaseous solute in the liquid solvent is equal to some constant times the partial pressure of the gas. Okay? So, which of the following statements is true? If we push the piston downward, that increases the pressure above the solution. These are directly proportional. As we increase this one, that's a constant. So if we increase this one, that one increases. This will cause, when the piston is pushed downward, this will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. No, the dissolved gas will go up. So the dissolved gas concentration will go down, A and B are false. Concentration of dissolved gas will go up, yes. But does the preceding statement make sense? This will cause the pressure of the gas to increase and the concentration to go up, yes. C is true. All right. 8. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? What do we know about the solubility of anything in a solvent? what we know is there are general trends, but we cannot predict with certainty any specific example. All right, keep that in mind as we read the statements. A, the solubility of a substance in water increases as the temperature rises, especially for gases. That's the killer. Especially for gases? No. As the temperature goes up, solubility of gases goes down. The solubility of a substance in water decreases as the temperature rises, especially for ionic solids. Well, as a general rule, the solubility of ionic solids goes up as the temperature increases, but not always. So, that one's false on its face. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That statement is true. And since A is false, then A and D can't be correct. So C has to be the answer. And skip down to 10. Okay, a solution contains 1 mole of liquid A and 3 moles of liquid B. All right, we've got a solution. And it's got 1 mole. Let's see, what are we going to do with it? Vapor pressure. So it needs to be sealed. Okay. 1 mole of A and 3 moles of B. Okay. This solution has a vapor pressure of 314 torr at 25 degrees. And it looks like the temperature is not changing, right? So 25 degrees is constant. This solution has a vapor pressure of 314 torr. All right. At 25 degrees, liquid A has a vapor pressure of 265 torr, and liquid B has a vapor pressure of 355 torr. What that means is the pure substances, A has 265 torr, and 355 torr. When they're pure. Okay, this is Raoult's law. The pressure above the solution, right? The pressure, total pressure, is equal to, right, this is Dalton's law of partial pressures first, is the partial pressure of A plus the partial pressure of B. Right, that's in solution. And the individual pressures are due to these pressures times the mole fractions of each one of those. So we could do that. I mean, we could calculate what is the partial pressure of this one due to its mole fraction, right? The mole fraction here is 0.25. Right. So the mole fraction of A times the pure A plus the mole fraction of B times the pure B. And that would be 0.25 for A times 265 plus 0.75 for 355 for B. Now, I don't think we need this, but it's a good exercise. So let's see, 0.25 times 265 is 66. Let's just round it off. Let's make it 3. 66.3 torr plus 0.75 and 355 times is 266.3. Let me see if I did that right again. Yeah. And then 66.3 is 333, rounded off. Right. So if this is a perfect mixture, then this value would be 333. Actually, oh, I worked this problem wrong in the worked problems. That needs to be repaired. This is the way to work the problem. This is the expected, right? And this is what you actually got. So this value is less than that value, which doesn't change the answer, but this is the correct way to work it. We're expecting this one if this is a perfect solution, where there's no interaction, either positive or negative, between the two members of that, two volatile members of that solution. We would expect 333, but it's less. So that means you're having an attraction between A and B in the solution. That's limiting the vaporization of either one. So let's see if we can find a statement that addresses that. This solution exhibits a positive deviation from Rayleigh law. No. This is the expected. It's negative. It's less than. This solution exhibits a negative deviation from Rayleigh's law. That is true. This solution is not ideal. If it were ideal, that value and that value would be equal. Okay. So that's why the answer is B. All right. Let's see. Skip 11, go to 12. A cucumber is placed in a concentrated salt solution. So what are we getting at here? A colligative property called osmotic pressure. If we place a cucumber in a concentrated salt solution, what will most likely happen? What can pass the membrane of a cucumber cell? Water. So which way is the water going to go? Water is going to go toward the more concentrated solution. It's going to go out of the cell. So water will flow from the cucumber to the solution. That's the answer. A. How about 13? Osmotic pressure depends on all but which of the following? Well, what's the formula for determining osmotic pressure? Pi, which is the symbol for osmotic pressure, is equal to molarity times the gas constant times the temperature. Okay? So what does it depend on? It depends on molarity, concentration, and temperature. Does it depend on atmospheric pressure? All of the following except. Which does it not depend on? It does not depend on atmospheric pressure. It depends on molarity and temperature. The ratio of moles of solute to solution volume, which is another way of saying molarity. Okay. So A is the one that doesn't matter. Osmotic pressure has, atmospheric pressure has no bearing on osmotic pressure. All righty. I'm getting there. 3:30. Okay, one more in the easy section, and then we'll go to moderate. Shaving cream is an example of which colloid type? Remember what a colloid is? I think of a colloid as a fake solution. It's not really a solution. It has some of the characteristics of a solution, like the solute does not separate. I should say it's not a solute, because that's for solutions. The suspended medium does not separate from the suspending medium. In that respect, it behaves like a solution. But it's not a solution because those individual particles are simply small enough to be suspended indefinitely, because there is sufficient energy in that suspending medium to transfer to the suspended medium and keep it in uniform concentration. So what kind of colloid is shaving cream? Well, you got a liquid and you have a gas. A gas suspended in a liquid is a foam. That's definition. All right. So what are these others? Aerosol could be a liquid or a solid in a gas. Emulsion is a liquid in a liquid. A sol is a solid in a liquid. And coagulate is not a colloid, right? Coagulate is destruction of a colloid. You remember one easy way to tell the difference between a solution and a colloid? I'm painting myself into a corner. It's the I can't remember the name now. Let's move on. So we're going to go to medium. And number 3. Okay. I just remembered it. How do you tell the difference between a colloid and a solution? The Tyndall effect. You shine a bright light through it. And if you can see the beam travel through the medium, then it's a colloid. If you can't see the beam, it's a solution. Okay, back to medium 3. A 0.2 molar solution of a solute X in benzene displays an osmotic pressure given by the formula pi equals 0.1 RT. Which of the following is most likely to be the case? Okay. Remember, actually, I didn't write the complete formula for osmotic pressure. I forgot that correction factor. Normally what we see is the effect of a solute on osmotic pressure is modified by this factor, and it's usually whole number, like 2, 3, 4, depending on how the solute dissociates as it goes into solution. But This question works the other way. If you form a 0.2 molar solution of X, but the correction factor is modifies this one, instead of 0.2 now, this is 0.1. That means I has to be equal to 1/2. So what does that mean? That means it's not dissociating as it goes into solution. It means it's forming associations, binary associations. So it's taking this concentration from 0.2 down to 0.1 and decreasing its osmotic strength. So the explanation is X exists in benzene as X2. Okay, it forms that bonding pair to decrease the concentration, and that in turn decreases the osmotic pressure by 1/2. Here, you want to go out? No. Okay, 4. Which of these solutions, 0.1 molal, 0.15 molal glucose, 0.1 molal calcium chloride would have the higher vapor pressure and the highest vapor pressure and the lowest boiling point? Okay. The highest vapor pressure, this is Rayleigh law with a volatile solvent and a non-volatile solute. So as you increase the concentration of the solute, you decrease the vapor pressure. So that's Roman numeral 1. So if we, let's see, let me write these up here. 0.1 molal sodium chloride, 0.15 molal glucose, and 0.1 molal calcium chloride. So Roman numeral 1 is vapor pressure. We want the highest vapor pressure, which means we want the lowest concentration of solute. So the lowest concentration of solute would be, this one is actually 0.2 molal because you have sodium chloride dissociating into 2. This one is 0.15, and this one is 0.3 molal because it breaks up into 3 parts. So the lowest, the highest vapor pressure would be this one. How about the lowest boiling point? The lowest boiling point is the one with the lowest concentration of solute, because as you increase the concentration, let's see, proportionality constant times molality. Now my mind's gone foggy again. Let's see. Yeah. Okay. As you If you increase the molality, you increase the boiling point. So we want the lowest boiling point. That means we want the lowest molality, which is also this one. So both glucose concentrations give us the correct answer for both of those conditions. Five. Oh, we're using the same. Okay. Maybe it's different questions for this one. So let's leave that one. Okay. All right, what's the question here? Which of these solutions, same ones, would have the lowest vapor pressure and the lowest boiling point? Okay, lowest boiling point, we got that one already. That's glucose. But the first one, the lowest vapor pressure, would have the highest solute concentration. This one. So this one is 1, and this one is 2. And the one that gives you that answer is C. There you go. Let me see how many we got to go. I need to take a bathroom break here. Just for a quick minute. I'll be right back. Okay. Let's see, where was I? Oh, is that all the medium ones? Yeah. Now we're in the difficult. Okay. Okay, in difficult, we're going to go down to number 2. Okay. Let's see. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute, okay, and 85 grams of water. The vapor pressure of the solution at 60 degrees Celsius is 132 torr. The vapor pressure of water, the solvent, is 150 torr. That's the pure solvent. What's the molar mass of the solute? All right. So let's go back to basics. The question is, what's the molar mass of the solute? So we need to know eventually the molar mass of the solute is equal to mass of the solute per moles of the solute. Right? That's what we need to know. Now, what do we know already? We know the mass, 53.8 grams. 53.8 grams. What we don't know yet is the moles of the solute. Okay. So okay, we can use Rayleigh law for a non-volatile solute. That means we only need to know the pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, and in this case, that's water. Okay, we know the vapor pressure. This is 132 torr. That's what we don't know. And we do know this one, which is 150 torr. So the mole fraction of water is 132 divided by 150, which is 0.880. That's the mole fraction of water. So we want to know how many moles. What does this mean? This means the moles of water divided by the total moles of, let's see, did we give it a solute? Okay. So how many moles of water do we have? Do we know that? Yeah, I mean, we can calculate it. 85 grams of water. Okay, so that's equal to 4.717 moles of water. So this is like 4.717 divided by 4.717 plus moles of the solute. So now we've got this equal to that, one unknown. We can solve for that unknown. And if we do that math, the moles of the solute equals 0.6432. So 0.6432 moles. And then this calculation, that calculation should give us 83.6 grams per mole, which is E. Pardon me. Okay, that was 2 Now we're going to go to 4. All right. There's 4. Let's see what we got here. You have a 10.4 gram mixture of table sugar and table salt. So the total mass is 10.4 grams, but we don't know what the composition is. We just know that we have sugar and salt together. When this mixture is dissolved in 150 grams of water, the freezing point is found to be minus 2.24 degrees Celsius. So that means we have depressed the freezing point by 2.24 degrees. That's delta T. What's the percent by mass of sugar in the original mixture? All right, so if we're talking about freezing point depression, that means we need this equation. Well, actually, it's going to be more complicated than that. Why? Because sodium chloride dissociates in solution and table sugar does not. So that's going to be a little trick that we have to introduce. The mixture, let's see, 10.40 grams is the total. Well, first of all, we need some information. Hello? Yes. Oh. Okay. February 19th. Okay, I'm gonna get my calendar out here. February 19th. Okay. What time would you like us? How about 9 o'clock? Cancel. Yes. Okay, 9 o'clock on the 19th of February. Okay. Okay, bye-bye. Sorry about that. That's another reason I hate working from home. Interruptions.
It don't bother me none, you're fine.
Let's see. And of course, I'll edit that out of the out of the final production. Let's see, 3 days. Let's see. And one other thing here. Okay. So back to our problem. The question is, what's the percent by mass of sugar in the original mixture? Well, in order to use this, we know that this is going to be 2.24 degrees, 2.24 degrees Celsius. And we know that the K, actually we have to look up the K for water. So the K for water, and it should be in useful information. Let me check to be sure. Let's see, K for water, water. There it is. No, that's not it. Here it is. The freezing point proportionality constant is 1.86 degrees C kilogram mole. 1.86 degrees C kilogram mole. Okay. What else do I need? The mass of water. So the mass of the solvent is 150 grams, which is 0.150 kilograms. Now, why do I say kilograms? Because that's kilograms. Okay, this is going to have a Van Hoff correction, but we don't know what it is yet because it'll depend on the ratio of sugar to salt. The Van Hoff correction for sodium chloride is 2, and the correction for sugar is 1. Let's see. I think we're eventually going to need to know the molar mass of each one, because this is related to moles, molality, moles. But the question is in percent by mass. So we might as well get the molar mass of each one. We're going to need it. So the molar mass of sodium chloride is equal to 58.44 grams per mole. And the molecular weight for sucrose is equal to 342.3 grams per mole. So we'll just keep that on the side here. Okay. All right, here's the trick. These solutes behave independently. So this value, this change in freezing point, can be seen as a summation of a change for each one, independent of each other. So this delta T total is equal to the change due to sucrose plus the change due to sodium chloride. That's how we get around this correction factor. So now we know that this one is equal to K molality of that times 1 for sucrose. Sucrose plus 2 times K molality of sodium chloride. All right. So we're going to have to use a little algebra here. 10.4 grams is the total. And what we're trying to get at is the mass percent of sucrose. So let's say if we know the total is going to be 10.4 grams, then let's let X equal the mass of sucrose or table sugar. If X equals the mass of sucrose, then 10.4 minus X equals the mass of sodium chloride. Okay. All right. So this expression, this delta T freezing point, we know that value is equal to 2.24. All right, that's not correct. I was starting to write something and I didn't finish it. So let's just say this is that value and this is that value. So this is 2.24 degrees C equals this K, which is the same for both of them. It's 1.86. And the molality is the number of moles of sucrose divided by 0.15 kilograms. Okay, that's this part. And this part is 2 times 1.86 times moles of sodium chloride divided by 0.15 kilograms. Okay. Now, I'm going to have to erase some of this. I can erase this much. We have this one converted to this one, so I can erase this. All right. Now, if I take this one and set it up so that I've got moles of sodium chloride and moles of sucrose on this side and put everything else on that side, this 1.86 divided by 1.5 can be factored out of this expression and that expression and put over here on this side. So what that's going to give me is 2.24 times 0.15 divided by 1.86. And that's equal to moles of sucrose here, plus 2 times moles of sodium chloride. Now, I couldn't factor the 2 out because I don't have a 2 over here, but I got a 1.86 and I got a 0.15, so I factored that out, put it on this side. And now that I've got that, I can erase this. And over here, this value reduces to 0.1860. And moles of sucrose is mass divided by molar mass. Right? If we took mass, grams of sucrose, and divide it by grams per mole, that'll give us moles. So that's the moles here. So what we have is the unknown X is the moles of sucrose. That's the mass of sucrose divided by 342.3. And then this one is 2 times 10.4 minus X divided by 58.44. Okay, now I've got to reduce all that and solve for the unknown. The unknown is, there's only one, it's X, so we can solve for X. And it turns out that X, we do all that legwork, is 5.6 grams of sucrose. And if we divide that by the total, 10.4 times 100, we get 53.8% sucrose. Okay. I know we had to go around the barn several times to get to that one, but it used a lot of different smaller pieces to get to the whole. Oh, that's it. That's all I have. Let's see, which one was it that I needed to correct? I got a big red circle. There it is. I'll hold that one out and fix that one. Because the way I've got it written here in work problems is wrong. It's got the same right answer. It just, I worked it wrong. So I'm going to fix that. Let's see, chapter 10. Yeah, that's together. And this is together. Okay. So when we come back next week, we'll have the first exam, and then we'll introduce chemical kinetics. That's your chapter 14, my chapter 12. And we'll have the whole class to take the exam and introduce the topic, because you guys are going to do the demo and create a report from the demo. So I'll send you both the same email, just as a reminder. And what I'll want from you is, when we meet next week, I want to see your lab notebooks, because I haven't checked them once yet. I need to see them at least once before we get going too far into the semester. And since the report will not be due until the following week, it won't be necessary for you to have seen the demo and put the information in. I just want to see the notebook set up.
Could you send me an example of that again? Because I really don't want to screw this one up.
Oh, how to set up the notebook?
Yeah.
Okay.
Because the last one I misunderstood it, and this one I really don't want to do the same thing again.
Okay.
I'm sorry about that.
I've done it several times already. It's your turn. Okay. So do you have trouble actually setting up the framework for the notebook? So on the front of your notebook, you have your name, you'll have the course and the semester at a minimum, to identify it as yours and what course it is and what semester you're taking the course. Then then you'll number all your pages. Right-facing pages are odd numbers. Left-facing pages are even numbers. So on the first, or you could skip the first one, you could say, let's skip to page 3. And you'll have the table of contents. And all you need down this side is page number. Starting page number, that's all you need. And here you have the title of the experiment. So you have there, and they'll match. Page number for this one, page number for that one. Because if you know where it starts, then if you have a page number for the second one, then you know the first one's over by then.
And I put everything at the front of the book though, right? Like the table of contents, I put it all at the front.
Right here. And then you go on down to your first experiment. Say you're going to
say where it's at on the table of contents. I put what page it is and what it's covering and everything.
let's say you skip down to page 7. So you have page 7 here, and you have your first one there, whatever the name is. And then you'll put the title here. And then you'll have, and this is on odd pages only.
Yeah, I know. That one I understood. That was the only one I did.
Okay. So you'll have the introduction. You know, what is it about this experiment why are we doing it? I mean, what are you supposed to gain from it? Introduction. Then you'll have a blurb on safety. Then you'll have materials. Then you'll have, let's see, intro, safety, materials. Now would be a good time for pre-lab questions, okay, if there are any. And then you could go in, you might have to skip to the next odd page, 9. And then you put in the procedure. Step by step, 1, 2, 3, what to do. And let's say we have to go to page 11 next to finish it out. After the procedure, you need a place for your data. Right? If the data is just a list, then you set aside a space for it. If you know from the method that you're going to be, say, for this one, you're going to be taking temperature measurements every 30 seconds, whatever the case may be, then you might write time here, and you do 0, 30, 60, whatever the case may be. It might be, I don't know if it's 30 seconds, it might be 10 seconds. That would make more sense. 10, 20, 30. And then over here, you would have temperature, degree C. And you would have a space for all that information.
Okay. I hope I can do it right this time. If I can't, then I guess I'll just have to fix it.
Okay. There's your data. Then you need a place for, let's say you're on page 13 by now. Then you need a place where you're going to show your calculations. And you leave a space for all your calculations. And then you'll have a page, I'm jumping around here. Maybe by the time you get to page 15, you need a place for summary and conclusions. And sometimes the summary and conclusions are buried in post-lab questions. So this may combine or may be separate post-lab questions. And you won't have all that information yet when you're filling out your setting up your lab book for that experiment, but you need to have a place
To put it.
Yeah, you need to have a place set aside for it.
Okay. See, okay.
And then once you get all that done, I wouldn't set up the second experiment until you're finished filling in this one, because you might have to bleed over into some more pages.
Yeah.
But that's what the odd pages are for.
And the even ones are for like the graphs and stuff like that.
I mean,
right?
even pages. That's what the even pages are for. Yeah, it's for overflow, extra information, corrections, big corrections. And when you write off these methods, the procedure, skip a line as you go down. That way, if you have just minor corrections, you can draw through it and make the correction on the spot right there in that line.
Okay. And then I make a new table of contents for the next lab.
No, use the same one.
Okay, I understand now, because that's what I did on the last notebook, because I kept making a new table of contents.
No, this is the one table of contents. And then you put the next experiment name here and the page it starts on.
Okay, I understand now.
Okay.
Thank you.
Okay, so let's see, did I cover all my points? Yeah, we'll introduce chemical kinetics, and then I'll give you the hard copy handout for the lab 2 that we'll have the following week. And the following week after that, the week after introduction, we'll do a review for a while, and then we'll go in the lab and do that experiment. And I'll have to bring a piece of equipment from Beckley, because you guys don't have a spectrophotometer, and we need that to make light measurements of our reaction vessel as the bleach works, because we're gonna.
That sounds like that's gonna be a unique experiment.
Oh yeah, it's fun. The real headache comes when you try to make sense of the data. So I'll help you with that too.
Okay.
And actually, it's already in Brightspace if you want to take a look at it later. But I wouldn't overlap too much, because we haven't even introduced the concepts of kinetics yet. We probably should do that before you get into the experiment. Okay, so I'll send you guys an email reminder that freezing point depression lab will be via demo, and then to have your notebooks ready for first inspection. And that's it, I guess. We're let's see, yeah, we're done a little bit early.